Hey everyone, if you've been following along with AI and large language models, you've probably heard the term RAG thrown around a lot. But here's the thing, RAG isn't just one thing. It's a whole family of architectures, each solving a different problem. Today, we're going to break down 10 types of RAG, from the simplest Hello World version all the way to powerful graph-based and agentic systems. First up, simple RAG. Think of this as the Hello World of RAG architectures. Here's how it works. A user asks a question. The system searches a database for relevant text chunks. Those chunks get stuffed directly into the prompt, and then the large language model uses that context to generate an answer. Clean, straightforward, easy to build, and honestly, it's a great starting point. If you're prototyping something, building a quick demo, testing an idea, simple RAG gets you moving fast. But, and this is a big but, it's usually not enough for production. It has no memory of past conversations, it can't handle complex multi-part questions well, and the retrieval quality can be hit or miss. Think of it as the foundation that everything else builds on. Now, what if your AI assistant could actually remember what you talked about 5 minutes ago? That's exactly what RAG with memory solves. It takes the simple RAG architecture and adds a memory layer on top. This layer persists context across turns in a conversation, so the system isn't starting from scratch every single time the user sends a new message. Imagine asking a follow-up question like, "Can you elaborate on the second point?" Without memory, the model has no idea what the second point was. With memory, it does. This is a simple but powerful upgrade, and it's one of the first things most production teams add after getting simple RAG working. Alright, now things start to get interesting. Picture this. A user asks, how does rising inflation in the US compare to Europe, and what policy responses have been most effective? That's not one question, that's three or four questions bundled together, and a single retrieval step is going to miss a lot. Branched RAG is built for exactly this scenario. It uses an LLM to decompose the user's complex question into multiple sub-questions. Then it runs parallel retrieval for each one, independently. And finally, it synthesizes all those separate results into one coherent, comprehensive answer. The result? Much better coverage, much richer answers, and the user doesn't have to know any of this is happening behind the scenes. Here's a subtle but important problem with standard RAG systems, and it has to do with embeddings. When you embed a question like, what causes inflation? The resulting vector looks very different from a document that explains inflation. They're semantically related, but numerically, they can be far apart in the embedding space. That gap hurts retrieval quality. HyDE, hypothetical document encoding, fixes this with a clever trick. Before retrieving anything, HyDE asks the LLM to generate a hypothetical answer to the question, even if it's not perfectly accurate. Then it embeds that hypothetical answer and uses it as the search vector. Why does this work? Because the generated answer looks much more like the target documents. It's phrased like a document, not like a question, so the retrieval becomes significantly more accurate. It's a small change with a surprisingly big impact. Not every question needs a database search. If someone asks, what's 2 plus 2, you really don't need to retrieve anything. But a naive RAG system would try anyway, wasting time and money. Adaptive RAG solves this with a routing layer. Before retrieval even begins, a lightweight classifier or LLM call evaluates the query and makes a decision. Does this need no retrieval at all? Does it need simple, single-step retrieval? Or does it require complex, multi-step retrieval? The system routes the query accordingly. This makes your pipeline smarter and significantly reduces operational costs, because you're not running expensive retrieval steps when they simply aren't needed. Adaptive RAG is one of those architectures that really pays off at scale. What happens when your retrieval returns garbage? Low quality documents, irrelevant chunks, things that have nothing to do with the question? A standard RAG system would just use them anyway, and you'd get a bad answer. Corrective RAG, or CRAG, adds a quality gate right after retrieval. After documents are retrieved, a scoring mechanism evaluates them. If they meet a confidence threshold, great, move forward. But if they fall below it, the system can reformulate the query and try again, or it can fall back to a web search to find better, fresher context. Only once high-quality context is confirmed Does the system proceed to generate the final answer? Think of Crag as a built-in fact checker for its own inputs. Crag checks quality before generation. Self-RAG goes even further. It checks quality during generation in real time. The LLM is trained or prompted to generate special reflection tokens as it writes its answer. These are essentially the model asking itself questions midstream. Do I even need retrieval for this part? Is this claim actually supported by the retrieved context? How confident am I in what I just said? If the answer to any of those is no or not very, the model can course correct before the response is even finished. The result is answers that are more accurate, better grounded in evidence, and much more transparent about uncertainty. Self-RAG is powerful for high-stakes domains. Now we're entering territory that starts to feel less like a pipeline and more like an actual thinking agent. Agentic RAG merges RAG with AI agents. Instead of following a fixed path, the LLM acts as an orchestrator. It decides its own next steps dynamically. Should I search the database for more context? Should I call an external API? Should I run some code to compute something? For complex queries, this loop can repeat multiple times, retrieving, evaluating, retrieving again, until the model decides the answer is good enough. This is a huge leap in capability. Agentic RAG can handle tasks that would completely break any fixed pipeline because it adapts to what the problem actually requires. The real world isn't just text. Business documents have charts, research papers have figures, presentations have diagrams and tables. Multimodal RAG brings all of that into the retrieval system. There are two main approaches. The first, use a vision language model during ingestion to generate text descriptions of images and charts, so they can be searched just like text. The second approach, store image embeddings natively alongside text embeddings and retrieve from both. Either way, the system understands your entire document. For industries where so much critical information lives in non-text formats, multimodal RAG is a game changer. Last but definitely not least, graph RAG. And this one is genuinely exciting. Standard RAG treats documents as a flat pile of chunks. Each chunk is independent. There's no explicit relationship between company A, person B, and event C, even if they appear together. Graph RAG changes that fundamentally. Instead of just chunking documents, it builds a knowledge graph on top of them, mapping entities and their relationships. Think, nodes for people, companies, concepts, and events, edges for the connections between them. When a query comes in, the system can traverse this graph. It connects dots across multiple documents in a way that flat vector search simply cannot. Ask a question that requires linking 5 different facts. GraphRag handles it. It dramatically outperforms traditional vector search on questions that require multi-hop reasoning, connecting multiple pieces of information together to reach an answer. All right, let's bring it all together. We started with simple RAG, added memory, used branched RAG for complex questions, and fixed embeddings with HyDE. We made systems smarter with adaptive RAG, added gates with corrective RAG, self-reflection with self-RAG, and dynamic reasoning with agentic RAG. Then we extended to visuals with multimodal and connected dots with graph RAG. Each of these architectures solves a real problem. If you found this useful, drop a comment below for deep dives. See you in the next one.